this stage. All right, so now let's take a look at this. Now, let's say I take a sample of that size, of a certain size. Let's see what's a good example I can use here. Before we move on to that, I wanted to mention, now I'll come back to this other part. Okay, so let's apply that now. I'm going to open up the first problem that we have that was in the exercises for the exam 2 practice that's up on Blackboard. Okay, so I'm going to take a look at this first problem that's here, and it has a sample. Let's see how many there are. What's our sample size here? Our sample size is 12 individuals. 12 randomly selected individuals were sampled. Blood glucose levels: 12 hospital patients 1 hour after receiving a new drug to control blood pressure. Blood glucose level is measured in milligrams per deciliters. Okay, so we found that these are the values for each individual person. The average for all of those 12 people was 106.17. The sample size is 12, of course, and the standard deviation turns out to be 23.24. Okay, so let's think about what that tells us now. That tells us that since we took a sample of size 12, okay, let me just copy this information here. Our sample size is 12. Our mean, X bar, is equal to 106. I'm going to round this off a little bit. In your case, if you're working on the exam, you're not going to round anything until you get to the very end of your calculations. And I'm going to call my standard deviation, I'm going to call it 24, to make things a little simpler. Okay, so now what this is telling us is that in this particular case, with this sample size, we found a mean of 106, which we think approximates the population mean. It's not equal to the population mean, right? Otherwise, we wouldn't have to bother with any of this stuff. It only approximates the population mean. Okay, and we got a standard deviation for this sample group, these 12 numbers, of 24. You guys remember how we calculated that? We found the difference between each individual value and the mean, squared the differences, added them up, divided by the number of degrees of freedom, or n minus 1, to get the variance, then took the square root of that to get the standard deviation, and so on and so on, and we came out with this number 24. Okay, so now that number is going to give us a clue as to how much variability that there is in repeated samples from this population of size 12. Well, you remember we decided that if I drew all the possible distribution, or the distribution of all the possible samples of size 12 for this particular population, well, I would expect the mean to be about the same as mu for all the repeated samples, right? And which I'm thinking X bar might approximate. And the spread, the standard deviation of all these samples, is going to be called standard error instead of standard deviation, is going to be equal to the standard deviation of the population divided by the square root of the sample size. Okay, so now I'm going to say to myself now, let's say for a moment that I know that the population standard deviation is equal to 24. I don't know the population standard deviation, do I? I actually only know the calculated standard deviation based on those 12 numbers, right? Which turned out to be actually 23 point something, but I'm assuming it's around 24. Okay, so let's say for a moment that this is really the standard deviation of the population. Standard error is going to be equal to 24 divided by the square root of 12. I'm going to pull up a calculator and calculate this out. Okay. Okay, so I got square root of 12. 12. Square root of 12 is 3.646, so on and so forth. Put that in memory for a second. Clear this. I got 22 divided by 3.46, so that's equal to 6.35. So the standard error is equal to 6.35. Okay, so now that tells me that 95% of the results of the sample means that I expect to get are going to be about two of these standard errors below what I found the mean, the population mean, and two and a half two above the population mean. Well, rather than look at it this way, I'm going to look at it another way. I'm going to say to myself, I think that the mean, I have an approximation that the mean x bar is equal to 106. And I'm saying to myself, well, gee, I want if I add two standard deviations to that number and subtract two standard deviations from that number, in other words, plus or minus the two times the standard error. Okay, if I multiply that out and add and subtract the standard error from what I think the mean is, then I figure I'll get 95, I'll have 95% certainty that I will get all of the samples if I started from the true population mean. I would get 95% of all the sample results within those two of sample size 12 within that boundary. Another way I could look at it is that I can be 95% certain that the real population mean is between these two numbers, between whatever two numbers that this comes up with. In other words, I can have a confidence interval that tells me I'm 95% sure that the population is within this number and this other number. Well, in actuality, if I know what the standard deviation of the population is, I can use the z-score here for 95%. Or another way to look at it is the z-score for alpha over 2. In other words, the z-score, alpha is my alpha error. Okay, if I want 95% certainty that I capture the mean, I'm willing to accept 5% chance of being wrong. In other words, 5% of the time, 2.5%, I'll be too low. The mean will actually be lower than I expected. 2.5%, the mean will actually be a percent of the time it'll actually be higher than I expected. So if I have an alpha of 5%, that's 95% confidence that I'll capture the mean. So very frequently that's described as z being a z representing alpha over 2. Well, alpha over 2 is 2.5%. Okay, remember at our chart, look what our z table looked like? It showed the value that was to the left of the z-value. So 2.5%, a z-score that would have a value that would make the left tail 2.5%. Well, that's the same thing as a z-score on the other end that would give us 2.5% with of a tail left at the other side. So the total error that you could have possible is 2.5% here and 2.5% here. So when you see when you're looking at 95% certainty or an alpha of 5%, you're looking for a z-score that gives you a single tail of alpha over 2 or 2.5%. That z that does that for you is equal to 1.96, either plus or minus, depending on where you are. I'm going to just show you that that really is true here. Okay, if I look for a 2.5%, the area of 2.5% in here, it's going to be right around here. Let's see. 2.5% is right there. And what does that represent? What's the z-score represents that? Negative 1.96, right? So that really does work. Okay, so I'm going to go back to what I got here. Okay, and so I'm going to say plus or minus 1.96 times the standard error, which is 6.35. Okay, so I'm going to say that this is roughly going to be about 12 and a half. Let's call it 12 and a half. So my confidence interval is going to be 106 plus minus 12 and a half and 106 plus 12 and a half. Okay, and that's going to come out to be roughly 119, 694, 93, roughly 93 to 119, right? So we're 95% sure, or we're willing to accept 5% chance of error that our A true population mean is between 96 and 115. That's how I calculate my confidence interval if I know the standard deviation of the population. Did I know the standard deviation of the population? Somebody said, what did I do wrong there? Somebody says not 22. Did I say 22? Somewhere in there? It's possible. Don't worry about it. Tolerate my error there, okay? So are we comfortable with that? In calculating the standard error, I said 1.96 times, what did I do over here? Oh, it's 24. You're absolutely right. Okay. Okay, thank you for pointing that out to me. Okay, right, exactly. Ben pointed out, we don't know the population standard deviation. I just made that up as if we knew it. Okay, but in fact, we do not